Hello everyone, welcome. My name is Harsha. This week's lecture will be looking into file I/O. First, we'll look into what is a file system. Next, we'll look at some common file system abstractions such as a file and a directory. Next, we'll look into the file system interface and some common file system operations. We'll also look into a very simple file system, which is a toned down version of modern day file systems. We'll also look into a couple of operations such as namely read and write on this very simple file system. We'll also see why these operations are really slow and how to speed them up. So what is a file system? So everybody must have heard about Unix's defining feature that everything is a file. By everything we mean network sockets, devices, data on disk, etc. are represented and manipulated as files. So file system is an implementation of the file interface. It basically decides how data is stored on the disk. The main attributes of any file system is that it should be high performant, be highly scalable and resilient to failures. Some common operations that every file system must provide include open, read and write. These operations allow us to open a file, read data from the file and write data back to the file. Some popular examples of a file system include ext4, which is used to store data on disk and manipulate data that is stored on a disk. This file system is present on almost all Linux systems. The other file systems that I've shown here, including procfs, sysfs and tempfs, are virtual file systems in the sense that they do not interact with data that is stored on the disk. Procfs and sysfs are used to control processes and provide information about all processes that are running on a system. Tempfs is an in-memory file system that is used to store temporary files. Next, let's look into file system abstractions. First, let's look into a file. A file is simply a linear array of bytes, and each file has a low-level name called the inode or inode number, to be more precise. Every inode is basically a structure that contains metadata about the file. This metadata could include information such as size, permissions of the file, and time information including the creation time, the last access time, and other information such as file type. The inodes also contains the locations of data of the file through direct or indirect pointers. This metadata information can be accessed via the stat system call. Moreover, files are created using the open system call, as we'll see later. The next abstraction that a file system provides is that of a directory. A directory also has an inode number. However, the contents of the directory are specific. They contain mappings between inodes and their names. So for example, if a directory has a file named foo whose inode number is 10, the directory would contain the mapping between foo and 10 as its data. A directory hierarchy is the organization of all files and trees, for all files and directories in a tree-like structure. The directory hierarchy begins at the root, represented by a slash, and a slash is used to separate subsequent directories and files. So for example, here we have a file called hello.txt which is located inside a directory called bar, which is in turn located inside a directory called foo, and this is how you would represent hello.txt using its absolute path notation. Next, let's look at the file system interface. The file system interface allows one to create files or directories and access those files or directories through read or write operations, and also delete those files or directories if required. Let's take a small detour and look at a tool called strace, which is basically a system called tracer. You must have read about this tool in the previous lecture, and you can refer to that lecture for more detail. In this figure, I have used strace to look at the system calls that are generated by a call to cat foo. So cat foo basically outputs the contents of foo to std out. So here we see a few file system operations or file system calls such as open, read, write. Next, let's look at the file system interface that is used for creating files. So files can be created using the open system call, which takes as its arguments a path name, a set of flags, and a mode. For example, to create a file, we would use the oCreate flag. And more flags and modes of operations can be found in the man pages for this open system call. Open returns a file descriptor, which is an integer. It allows you to perform certain operations on the file, and the file descriptor is managed by the OS on a per process basis. The file descriptor is an index into a global or open file table, and the open file table has one entry for each open call. Every process has three file descriptors, the stdin, stdout, and stderror, which are represented by file descriptors 0, 1, and 2 respectively. Next, let's look at the file system interface for reading and writing to files. So on this slide, we see four system calls. So the first system call is the read system call, which basically reads certain amount of data into a buffer from a file that is represented by the file descriptor ft and returns a number of bytes that are read. And the write system call does the opposite. It basically writes data from a buffer into a file that is represented by ft and returns a number of bytes that are actually written. And we have other system calls such as the lseek call, which is used to change the read or write offset into the file. Again, this offset is tracked by the OS for every open file. And finally, we have the fsync system call, which forces all dirty data to be written to the disk. And this system call is useless sometimes as it doesn't perform as required. And there's a lot of debate, especially by developers of Postgres. You can take a look at that debate by following the link shown here. There are many more file system calls to be considered. We won't have time to go into them, but a few of them are shown on this slide. These include rename, which is used for renaming files. Stat, as we discussed before, is used to get the metadata information about files. mkdir, it's used to make directories. Read directories is to read information and data from a directory. Unlink is used to delete files, and rmdir is used to delete directories. Next, let's look into why the removal of file is called as unlink. So we can create file system entries using the link system call or by invoking the command line tool called ln. ln takes two arguments. One is the old path name and second is the new path name. And what it does is it creates a link between the new path name and the old path name. And this is termed as a hard link because you just create another name for the same inode and no file data is copied. And finally, the file is deleted only if the number of links is 0. However, the drawback of a hard link is that you cannot hard link to a directory or to files that are located in other disk partitions. Hence, we have a second kind of link called symbolic links or soft links, which is created by passing the -s option to ln. The symbolic link itself in itself is a special file that contains the path name of the target file as its data. Next, let's look at how we can make a file system and mount it. So on Linux systems, we have this tool called makefs, which basically takes as input a device and a file system type. It writes an empty file system onto that device. And the second operation is of mount. So once we have the file system ready, we need to make that file system available within the file system tree at an existing directory. This directory is called the mount point, and we would use the mount utility for that. Next, let's take a look into the design of a very simple file system. But before that, let's take a look into a few of our assumptions. We assume that the storage device presents itself as a set of blocks that are logically addressable from 0 to n-1, where n is the total number of blocks, and this is how many of the modern day storage devices present themselves. We also assume that each block is of size 4 KB, and we also assume that the total number of blocks is 8. So we have a very small file system, which is just 32 KB in size. We also assume that the inode is 256 bytes in size. Next, let's take a look into the organization of this very simple file system. So we have a total of 8 blocks, and we need to divide them into the following. So we have 4 data blocks, one inode block, one block to store the inode bitmaps, and one block to store the data bitmaps. These bitmaps are used for free space management, which we'll talk about later. And we need one block to store the super block of the system. The super block is basically it contains the metadata of the file system, and it is present in a known location. So the for OS, before mounting the file system, it reads the super block and then proceeds to mounting the system. Super block contains information such as number of inodes, number of data blocks, block size, etc. Next, let's take a look at the contents of the inode. So the inode, it contains file metadata. This metadata could include the type of file, size of the file, the number of data blocks that are a part of the file. It will contain production information of the file, and also time information, which could include things like access time, modified time, etc. It also contains data blocks information, basically which data blocks belong to this file, and this information is maintained through either direct or indirect pointers. So in direct pointers, the inode stores the locations of data blocks directly, whereas in indirect pointers, the inode stores the location of blocks that contain pointers to other data blocks. Next, let's take a look at how the directory is represented in such a file system. So the directory is, again, it's another inode whose type is directory. This inode, it contains pointers to data blocks, and the data blocks, they contain a mapping between the file inode number and the file name. So as we saw before, there were 2 blocks that were reserved for bitmaps to track free inodes and data blocks. So basically, if a bit is set, it indicates that the inode or the data block is used up. So there's the inode bitmap to track free inodes and the data bitmap to track the free data blocks. This information is used by the file system when it needs to allocate new blocks for new file system data. Next, let's look at the read operation on the very simple file system. Let's assume we want to open a file named bar. It's located in the directory name foo, which in turn is located in the directory named root. We would like to read the data from the file, and we assume that the file is of size 8 KB or 2 data blocks in our system. So consider this diagram, which shows the system calls on the leftmost column. This operation, read operation, consists entirely of open and read system calls. So since the file is located in a directory named bar, which in turn is located in a directory named, the file is located in a directory named foo, which in turn is located in a directory named root, we first need to read the root inode into main memory, from which we figure out the location of the root data blocks, and then we read that into main memory. From the root data block, we figure out the inode of the directory foo, and then we read that into main memory. Once we read that into main memory, we then figure out the location of foo's data and read that into memory. And from foo's data, we figure out the inode number of bar and then read that into main memory. And next, we try to read in the file. So first, we read in the bars inode. By reading the bars inode, we figure out the location of the bars data blocks, and then we read in the data block number 0, and then we write back to the inode. So basically in this case, we update the inode with the access time of the file. Next, we read in the bars inode again to figure out the data block number 1 location. Then we read in the data block 1, and then we update the bar inode with the access time. Next, let's take a look at the write operation in the very simple file system. We would like to create a file name called bar located in the directory called foo. We would like to write to the file, and let's just assume that we write a single block of data, which is just 4 KB of data to the file, and then we just close the file. Consider this figure, which shows the system calls in the leftmost column. So in this operation, we just have two system calls. One is create and other is write. So first we read in the root inode, and then the root inode basically contains again data pointers to the root data. So we read in the root data. Next we read in foo's inode, and then we read in foo's data. And then next we read in the inode bitmap. So in this case, we would like to figure out, since we're creating a new file, we need to figure out which inode is free. So hence we read in the inode bitmap to figure that out. And then we write to the inode bitmap after we choose one free inode for our file named bar. Next, we write to foo. So basically here we create an entry or a mapping between bar and its inode number. And then we read bar's inode, which is basically garbage now. And then we write to it. We write the bar's metadata information. We create a new inode and write it back to the bar's inode. And then we update foo's inode correspondingly. And during the write operation, we read in the bars inode and to figure out basically the free data blocks that are associated with the bar file. And then we read in the data bitmap to figure out the free data blocks that are present in the file system. And then we pick one data block and mark that as used. And then we write data to the data block, and then we update the bar inode to reflect that information. Next, let's look into why our simple file system is not ideal in terms of performance, and why the performance could be really poor. So we see that during the read and write operations, we request the same data blocks from disk repeatedly, and also make the observation that reading from disk is a slow operation compared to reading from memory. And the solution adopted by many modern operating systems is to cache the data blocks in main memory. So the strategy, the OS also needs to decide which blocks to keep and which blocks to evict from memory to make space for new data blocks to be brought into main memory. So it uses the one example policy could be the LRU policy, for example, in which case the OS evicts the least recently used block to make space for new data blocks to be cached into main memory. Also, modern operating systems integrate virtual memory pages and file system pages into a unified page cache. The same same set of operations occur during writes. So instead of immediately processing writes, they are buffered into main memory. So the advantage of buffering writes is that you could write in batches. You could also have a better scheduling of I/O operations since they are very slow, and you could also avoid writes together. For example, if you create and delete a file immediately, then you don't have to update any of these on-disk file structures. So in that way, you would entirely avoid writing. With this, we come to the end of the lecture on file I/O. See you all in the next lecture.